x4, this is 0. Whenever you see a term like this, that the summation of powers gets you beyond k, this is 0, okay? Because we're focusing now on the nilpotent version of it. So this is all polynomials, non-commutative. Now here we're focusing on the ones that are nilpotent of order k, which means the ones that anything degree k plus 1 vanishes, okay? So for these guys we can introduce a basis. Actually the p-hole basis works very nicely. It doesn't matter because the p-hole basis is general. For any Lie algebra, and this is a Lie algebra, it's guys that I can multiply and I have a Lie bracket for them. So the p-hole basis, whenever you have a Lie bracket, a Lie algebra, gives you basis for this Lie algebra. And it just depends on number of indeterminates, the number of the variables, and the order of nilpotency. Okay? Okay. So here we can define actually an exponential map. So if you have a z, any element z, any polynomial in the Lie algebra, any polynomial, we will define here, e to the z to be 1, the polynomial that is 1, plus this, the z, the polynomial itself, plus z squared. How you get this z squared? Well, we can multiply, that's fine. And yada yada, z squared over square root 2. So this is an exponential map. It might cause a problem if we are not truncating, so this is why they call it formal power series. But we don't need to worry about that because we're going to truncate anyway. Why? Because we're working with nilpotent system, right? Nilpotency will come and say anything that is beyond k, anything that is degree k plus 1 will naturally vanish, okay? So the nilpotency will cut this and we have a finite number of terms, so no need to worry about conversions or anything, it's well defined. This is the exponential map. So this actually is tempting to define a differential equation because we have an exponential map. How are you going to define your differential equation? We define this as s dot equals s times z. These are two polynomials, okay? With initial condition s0, some polynomial. Actually, the solution s of t is, as expected, s naught as a polynomial multiplied by e to the tz. So this guy, exponential of tz, z is a polynomial, okay? Exponential of a polynomial, according to this definition, is a polynomial, right? I have now a polynomial and the initial polynomial, I can multiply them. So at any time, I have a polynomial. This is how your polynomial s evolves with time. So you have s naught, and this s naught you keep multiplying by z, and change s by this rate. So the solution of this differential equation is this guy, which is, you know, it's, if you look at it, you might feel, oh, it's very familiar because it's a linear differential equation and the solution is exponential. So this seems matching our intuition. But anyway, this is the exact solution, okay? Any question about that?
Professor, the order matters, right? Like
yes, sure. So this is why this is the right order.
Right.
Yeah. They are non-commutative, and this thing that we need to take care of very much because it's the basis of everything, right? Okay, so this is why actually sometimes we call this z as polynomial input. It's as if this is the input to this differential equation. We're gonna worry about this later, not now. Okay, so if you have this, since we defined already the exponential map, if you have x and y polynomials, I can do this. And obviously they don't commute, right? And neither of them is equal to what we can expect from regular things, right? These guys don't commute. And it's easy to show, like expand e to the x from the definition, e to the y from the definition, multiply them together, and do the same here. They are not the same. Why? Because whenever you have x and y multiply is different from y times x. Or just you know, an overview here. These guys commute here in the exponent because it's addition, but these guys don't commute. So I can swap here, but I cannot swap there. So obviously they are not equal. So this raises the following question. I'm just introducing you to the theory, okay? So I'm giving you the facts from the theory. But if you have any question, just stop me. Why this is this case or whatever. The question is, well, okay, if you have e to the x and e to the y, I cannot swap, I understand. Is this equal to some e to the z for some z in the Lie algebra? This question was there for a long time in literature, and the answer came by the very famous formula of Campbell, Baker, Hausdorff formula. So what does it say? It says, again, this is very generic. It's for any Lie algebra. I really don't care about the x's. The x's are indeterminates, to be determined later. They can be matrices, polynomials, vector fields, whatever you like. So this is very generic. If you have e to the x, e to the y, this is equal to e to the x plus y as expected, but of course more, because it's non-commutative. 1/2 the Lie bracket, it's for the algebra, plus 1/12 xxy minus yxy, and yeah, the higher order terms. And you can get the higher order terms from the basic definition. Expand this as an exponential, exponential, multiply, equate coefficients. You get the remaining terms if you're interested in them. Okay. So this was a very important formula. I'm going to see how we're going to apply it today. But if now we define now this set of elements, every exponential of z such that z in your Lie k of x1 and xm. So what's that? Let's just focus here on a minute. So this is almost all our polynomials in the Lie algebra, right? And this is the Lie algebra itself, which means it's linear combinations of them. So polynomials and linear combinations of them, okay? And it's the Lie algebra, which means it's polynomials, linear combinations of them. It's Lie brackets of the polynomials, linear combination of them. All these combinations, but it's up to k. Everything else vanish. Take any polynomial, if you exponentiate it, flow along the vector field or something, right? This is your set. All flows. So the claim is actually Gk is group under multiplication. And you can show it very easy. How you're going to show it's the group under multiplication, that whenever you multiply two elements in the group, you get an element in the group, which means exponential of something. Is this true?
Yes.
Why? This is the Campbell-Baker-Hausdorff formula. So this is really a group. This is really closed under multiplication. And if we show this is easy, right? So we have an inverse element and identity element for the multiplication. So yeah, it's a group. It's actually a Lie group because it's a group and the manifold, but we'll not go in this direction. But here is a very interesting result out of all this, and this is the final thing that I'm going to mention, that any element, any S in that group, it can be written S as, remember this is a Lie algebra, right? So this is the exponential of any element in the Lie algebra, and the Lie algebra, it has B whole bases, right? So it M and K is B1 up to Bs. Okay? So this guy, any element in the group can be written as, I don't care where do you come from, I don't care how did you arrive at this guy. Because remember, how we arrive at elements here, exponentials of elements. Okay? So you can keep exponentiating, I don't care how you arrived here, but any element can be written as this form, which means it can be written as exponentials of this Lie brackets only. I don't care where you come from, how did you construct this point. If it's a feasible point, then it must come from, or it can be constructed by flows along these Lie brackets and the B whole basis. Okay? Any question about that? Well, this is a result. This is a main result. But of course, I didn't discuss how they proved it, but is it clear or not to you, the result itself? Okay, so that's enough for here, because we had a lot. So let's go back and see why we care about all these, right? Why this really matters to us in our language, how we can project this to our language, okay? So for example, instead of the set of non-commutative polynomials, we have our Lie brackets. So we have our G1 up to Gm. They live in the set of vector fields on N, right? And we know that this guy is indeed a Lie algebra, because it's a vector space. It's vectors, a bunch of vectors, of course. And we have a Lie bracket, vectors and Lie brackets. So this is a Lie algebra. And in our language, I forgot to disable this thing. Yes, go ahead, Mama.
The set of all vector fields on the manifold is a Lie algebra?
Yeah, it's a vector space, right? And it has a Lie bracket. What's the problem with that?
Okay.
Yeah. So we showed it before. We discussed this before. So we have this. What about the multiplication and the commutativity? Well, we defined before, what do you mean by G1 times G2? Well, viewing a vector field as a derivation, right? We already defined this before. These guys should act on F. So this is actually the definition of this guy is LG1, LG2, F. And we know that this is really different from G2 acting on G1, F, right? So, and if you want to write it in coordinates, just computation for the sake of computation, this guy is really nothing but the gradient of G2 as a matrix. This is the Jacobian times G1, at least on Rn. And this is the Jacobian of G1 times G2. Obviously, they are not the same. Okay, so this is our multiplication language in Lie brackets. Well, it does. I have complete freedom to define multiplication. I can define the multiplication the way I like, right? So this is the way we define multiplication for vector fields. And if we define multiplication for vector fields this way, obviously it's non-commutative, and now the Lie bracket is exactly the same definition, right? It's exactly the same definition. Our Lie bracket for vector fields is this guy minus this guy, right? So it's exactly equal to the same definition for the Lie bracket here. Any question about that? Any questions so far?
Should that G1 be G2?
Yes. Any questions? Okay, so like I said, a vector space with the Lie bracket, we have Lie algebra. We already said that, so this is the Lie infinity of G1 up to Gm. It's actually a Lie algebra by itself, or Lie subalgebra of the vector fields. So this is a Lie algebra by itself, okay? The nilpotent version of it, it's the Lie k, okay, it's, everything goes hand by hand with this theory, okay? We have this exact same B whole basis, right? Any question so far? A vector field on a manifold gives rise to what? So Z in L-infinity, G1, Gm, or just on the manifold, a vector field. Any vector field, doesn't matter. Z gives rise to what? To a differential equation, right? X dot of t is Z, this is a nonlinear valued function. X dot equals f of x, or Z of x, right? X of 0 is x naught, correct? What's the solution of this guy? Well, if it's ax, I know it's e to the a tx, right? X naught. But this is a nonlinear. What's the solution? Anybody has seen it before? Well, we have Fleece expansion, which is very nice. This is 1983. It's very related to Volterra series, and with my ignorance, I just see it nothing but the Fourier series expansion of the flow. There might be some catch I don't know about, but if you see it here, x of t, I can write it as my initial value, and this is a very nice formula to solve your differential equation. Solve your differential equation plus x naught plus your first derivative, which is z, right? Evaluated at x naught times t plus your x double dot. Go and get your x double dot. You will find it as nabla z, the gradient, times z at x naught times t squared over 2 plus yada yada. It's very nice expansion. You can solve nonlinear differential equations, I don't care, with this expansion, right? So x of t is, I'm going to take x naught as a common factor, so the first term is identity acting on x naught, right? Plus the second term is z acting on x naught times t, plus, can you give me an expression for this guy in our language that we just set up? Can you give me an expression for this guy?
Z squared.
This is z squared indeed, right? If you apply here, this is z squared. So this is z squared in our language, and z cubed will be the nabla of the z squared times z, and so and so. Z squared t squared over 2 plus yada yada. This is all acting on x naught. Obviously, this is the exact same definition, e to the tz, like the exponential map over there, right? With the multiplication, everything flows out of the multiplication. You define your multiplication,